color, okay? All right, so you guys, we're going to be talking about section 8.6 today, and it's geometric sequences. Now, it sounds brutally difficult, but I'm here to tell you right now, it's super easy. Did you talk to anybody from second hour?
Yup.
And what'd they say?
They said it was the hardest thing they've ever done.
You did not talk to them.
You're right.
I'm
Okay.
on number 19 and I have 10 minutes to do it. So.
All right, so here's what we're gonna do. Before we start with geometric sequences, we're gonna go back in time. I don't know how long ago it was, but I taught you something else. It was called arithmetic sequences. And arithmetic sequences and geometric sequences have something in common. They're both sequences. And sequences is just a fancy name for a pattern of numbers, okay? So let's do so an arithmetic sequence is a sequence of numbers. So let's say I do this 3, 7, 11, 15. What's going on there? 3, 7, 11, 15. What's happening?
You're adding.
Yep, Nash. We're adding 4 to the previous number to get to the next number. That's an arithmetic sequence. So when you add a consistent number over and over and over again to get to the next term, that's called arithmetic sequence. Okay? So when you're adding a number, and that number is called the common difference. Okay? Today, we're not going to talk about arithmetic sequences. We're going to talk about geometric sequences.
Oh,
Well, yes, because I'm reminding you of the arithmetic, but we're learning about geometric. A geometric sequence is a pattern of numbers, a list of numbers that looks like, let's see. What's going on there?
you times these by 2.
We're multiplying by 2. So every term gets multiplied by 2, and that gives us the next term in the pattern. So it's a consistent number that's being multiplied. That's what makes it a geometric sequence. The number that we consistently multiply over and over and over again is called the common ratio. All right, so when it's an arithmetic sequence you add, it's called the difference. When it's a geometric sequence, you multiply, and it is a ratio. Okay, so far you're with me? All right, so what are our objectives today, since we're going to be talking about these geometric sequences? We're going to form geometric sequences. We're going to use formulas when describing geometric sequences. So this is the good stuff. That makes it algebra when
I
we
don't
use
like
formulas. You're gonna like this one.
I hate it.
You're gonna like this one. Just you gotta trust me on this one, okay? And you're bound to have a bad attitude before we even begin.
You call me evil.
So every single one of these examples is going to be like the problems you have on your assignment today. Now, the reason that's important is because watch what we do on our examples, because that's going to help you to know what to do on your homework, right? So example 1 says find the common ratio of each sequence. Bo?
We're timesing by 4.
We're timesing by 4 because 3 times 4 equals 12. 4 times 4 or 12 times 4 equals 48. 48 times 4 equals 192. Okay, so we're multiplying by 4 every single time. Now that's a pretty easy one to spot right off the bat, right? Like you can see it, you can see what's going on without any trouble. Not all of them are this obvious. Okay, so I'm going to give you another way to find this common ratio. if it's not obvious, like this one. If you take the second term, you may want to write this down. Take the second term and divide it by the first term. That will give you that common ratio.
That's kind of the formula I use, like on the one side, like for like
When it's,
decimals,
yeah,
I use.
that's exactly what you do. So if I hadn't seen this from trying to figure out, okay, 3 times what equals 12, I could go backwards and say 12 divided by 3, that equals 4. That's my common ratio. Okay, so if we look at letter B, it's not quite as obvious, is it?
No.
80, 20, 5, 5/4. So Zoe, what should we do?
20 divided by 80 is
1/4. Now I could leave it as a fraction or I could write it as a decimal 0.25. Either way, it still gives me the same value, right? That's my common ratio. So example 1, pretty easy, right? Let's keep going. We have example 2. It says find the next 3 terms of each sequence. Well, in order to know what we're doing, we have to, or what numbers we're going to get, we need to know what that common ratio is first, right? So the common ratio would be, say, take the second term divided by the first term. So we're multiplying by 3. So that means to get this term right here, I'm going to take 27 times 3, which is
81.
81. To get the next term, I take 81 times 3.
243.
To get the next term, I'm going to take 81 times, or 243 times 3.
729.
Okay. So far, pretty easy, right?
Yeah.
Good. It's going to stay pretty easy. Yay, this is a Good Friday assignment. Okay, so let's take a look at letter B. I'm going to switch colors. Okay, so we have negative, or we have 120, then we have negative 60, then we have 30, then we have negative 15. Notice it's going back and forth between positive, negative. Whew. So what should I do to find the common ratio, Brecken?
We need to subtract 75.
Wait, we're on B right here. Remember, geometric sequence is found by multiplying. So we're going to do this right here. Take the second term and divide it by the first term. What's the second term? Second term in this problem. Anybody? What's the second term in this problem?
negative 60.
Negative 60. What is the first term in this problem, Ethan? The first term in the circled blue problem. Yep, so we're going to take negative 60 divided by 120. And what does that give me? Audrey?
-2.
Almost. Negative 1/2.
Oh.
Okay, you guys? Beauty of this is you can use your calculator, let the calculator do all the hard work, okay? So negative 1/2 is not my answer.
No, because you gotta.
Negative 1/2 is the tool to get to the answer. So I'm going to take negative 15 times my common ratio. So negative 15 times negative 1/2. Now you see why calculators are helpful.
Yeah.
All right, Cooper, what do you get? Negative 15 times negative 1/2. 7.5, but that's only my first one. I need 2 more. So now I'm going to take 7.5 times negative 1/2. Scott, what do I get from that? 7.5.
I don't have my
You don't, okay, Brecken, you have a calculator. What's 7.5 times -1/2? You find it?
3.75.
Negative.
-3.75. Good. Now, Brecken, if you want to give me the next one, you can. What's -3.75 times -1/2? Well, you can multiply it by -0.5. So -3.75 times -0.5.
Wouldn't that be 8.7?
No, you're not dividing. You're multiplying. So -3.75 times -0.5. Yep, that's exactly right. Okay, so notice the pattern kept going, positive, negative, positive, negative, positive, negative, and it kept going down. If all of a sudden it changes and it starts going up, you guys say, I must have hit multiply when I should have hit divide, or divide when I should have hit multiply.
What's the last one?
1.875. All right, you guys, I'm gonna clear this out so we can do this last one. And no, I can't circle it, make a lasso and get rid of it altogether. I tried. Because the iPad is so older than the cells. Okay. So now we have 1.1, we're gonna see. 1.1, 2.2, 4.4, 8.8. What is my common ratio? Yes, Abby. Well, what's 2.2 divided by 1.1? Is it? It's just 2. 2, because you double 1.1 and you get 2.2. Okay, so our common ratio is 2. So now I take my last term, which is 8.8, and I'm going to multiply it by 2. What do I get? You guys, calculators are so helpful. 16. Nash? Yes. All right, now we take 17.6 and we multiply that by 2. 17.6 times 2. All right, Bo?
35.2.
35.2. And then we take 35.2 times 2. And Brecken, what do we get?
70.4.
Okay. Again, something that is not that bad if you have a calculator. Otherwise, you have to do a lot of stuff on here. Okay, now, example 3 asks us to tell whether it's an arithmetic sequence or a geometric sequence. Arithmetic or geometric? What do I know about arithmetic sequences? Let's see, Sam, what do I know about arithmetic sequences? Anthony, what do you know? Austin, what do you know? Nobody pay attention to anything I say ever?
Good question.
Mason, arithmetic sequence. What do you know about arithmetic sequences? Isabel, what do you know about arithmetic sequences? You add to get to the next term. All right, now let's try one of you guys that I tried before. What's a geometric sequence? What do you know about geometric sequences? Please tell me you know something, because it's what this whole lesson has been about. Yes. You multiply to get to the next term. Oh my word, I thought this was an easy one.
That wasn't easy.
So, letter A, is that a geometric sequence or an arithmetic sequence?
D.
Okay, everybody should have an A or a G, okay? So let's do this. A or G? A or G? Oh, way to cheat, guys. Dustin, you have to have some kind of an idea. It's a 50-50 shot here.
Or.
Hey, you guys, it's an arithmetic sequence. What is it that we're adding each time? Positive 2, actually. Okay, so this is an arithmetic sequence. What about letter B? 56 to 28 to 14 to 7. Is that an arithmetic sequence or a geometric sequence? Arithmetic or geometric? Do you add to get to the next term or do you multiply to get to the next term? Let me just say, if you're dividing, you're still multiplying. If you're subtracting, you're still adding. Do you know what I mean by that?
Yep, I do.
Okay, it is a geometric for those of you who are holding up 2 fingers, because we are actually multiplying by 1/2. Okay, dividing by 2 is the same as multiplying by 1/2. Okay, now this is where it gets algebraic. That was the easy part, guys. This is actually still not hard, so don't stress yet about it. It's really not that bad.
I didn't suggest it.
Okay.
I did all do it.
So let's just pull back to this guy right here. Hello. There we go. So remember this one? We had 1.1, 2.2, 4.4, 8.8. Then we figured out the next 3.
Better save my battery.
So because this was the first term, this was the second term, this was the third term, fourth term, fifth term, sixth term, seventh term. Now, that wasn't too bad. But what if, instead of finding the next 3 terms, we were asked to find the 24th term?
You have to use a formula.
Well, we could keep multiplying by 2 over and over and over again, but there's got to be an easier way. There is. It's called the formula. Now, I know it's kind of messing with all my little drawings here, but let me rewrite it. So this is the first term of any sequence. Okay, so that's the first term. This right here is your common ratio. So the A is your first term. The R is the number you're multiplying by. And the N right up here is the term number that you want. So if we were to write this sequence into a formula, we would use A of N equals, what's the first term? Dash 1.1. What's the common ratio? What do we multiply by over and over and over again? 2. We want the 24th term, right? So that's N. And then it says 24 minus 1. Now we use PEMDAS. PEMDAS says we should always do exponents before we multiply. So let's simplify this first. So we have 2 to the 23rd power. And then we're going to take that number and multiply it by 1.1. So 2 to the 23rd power, I'm going to do that on my camp.
I'm gonna do it too.
All right, you do it. I'll see if you're right. Or you can see if I'm right.
Wait. What was
It's 2 to the 23rd power.
it?
And I'm getting a really large number. It is
Me also.
8388.
608.
Right, but that's before I multiply it by 1.1. Yeah, you could have used scientific on this. So it's 922.7468.8. Now, that formula saved us a whole lot of time over trying to multiply and getting those 24 terms out until we got to the 24th term. Does that make sense? In second hour, I just made up, I said, oh, let's find the 73rd term. Ah, youch, that would have been even more painful, right? Using the formula, however, it wasn't bad.
That's only the 24th term.
That's the 24th term. The 73rd term ended up coming out in scientific notation because it was so huge. All right, so you guys, here's what we're going to do with it. If we look at example 4, let's switch colors. Says find the first, the fifth, and the 10th terms of the sequence that has the rule a of n equals 5 times -2 to the n minus 1.
First one.
All right, now it says find the first,
Uh,
the fifth, and the 10th. So how many answers are we going to have?
3.
3 answers.
The
We're
first
gonna
one's
have
10.
one. The answer for 1. We're going to have the answer for 5, and we're going to have the answer for 10. What we're going to do is we're going to plug those in right here for n and solve them out one at a time. Does that make sense? So in a sense, it's almost like a t-table. See that?
Uh-huh.
Here's our n. Here's our equation. A of n equals negative. Oh, it's going to be small. Negative. Okay. -2. Wait, it's not even -2. -5. No, it's not even negative. Wow. 5 times -2 to the n minus 1. Okay, and then this is our a of n. So we're going to put 1 in here. So we're going to have 5 times -2 to the 1 minus 1. What's 1 minus 1?
0.
So what's 5 times -2 to the 0? 5. Because -2 to the 0 is 1. 1 times 5 is 5. Your calculator would do this for you, by the way.
So it's 5.
Yep. And look. I don't know why it keeps switching. If you notice, remember our equation? Remember the equation? This guy is always the first term. So we didn't even have to do the math if we recognize that this is always the first term. Okay, now we're going to plug in 5 for n. So that's going to be 5 times -2 to the 5 minus 1. So I'm going to have 5 times, what's -2 times -2 times -2 times -2?
-2, so it'll be 4. We can do -2.
32.
-8.
What, 1 too far?
16.
16. So what's 5 times 16?
72. 80.
80. Now we're going to plug in 10. So we put 10 there. 5 times -2 to the 10 minus 1. So we're going to take -2 9 times.
-5,
6, 7,
96.
8, 9, and then multiply it by 5. Okay, what is it? 2 to the 9, -2 to the 9. I'm getting 2560. -2560. -2 to the 9th was -512. -512 times 10, I mean 5, is -2,560. Is that confusing?
No.
You're just plugging each one of these numbers in for that end,
Okay.
right here. One at a time. Find it, and then go on to the next number. Okay?
Do we
Yeah.
have to do that last one?
We do have to do the last one.
Oh.
It's fun. It's all good.
Oh, we don't have any word problem. That's the thing.
It's a good one, so let's do it. Okay, so you drop a rubber ball from a height of 1 meter and it bounces back to lower and lower heights. Each curved path has 80% the height of the previous path. Okay, so now what that looks like is this. You drop a ball like that. It's gonna bounce back, but not at its full height, right? So then it bounces and then it comes back up like this. Does that make sense? Until it gets down to nothing. The original height was 1 meter. What is that in centimeters? So we had 100 centimeters, we'll call it our first term. What would the next term be? How far would it have come back? 80. Then what would be the next number?
60.
It isn't though.
Oh,
Nice try though. I'm glad you tried. Because 80% of 100 was 80, but what's 80% of 80?
Yes.
You guys have calculators. What's 0.8 times 80? 64. Then we would find 0.8 times 64. 51.2. Then we would find 0.8 times 51.2. 40.96. That's 1, 2, 3, 4, 5. That would be our fifth path. If we wanted to do this with the formula rather than figure it out, because what if they wanted the 12th path instead of the 5th path? Then we would have set up an equation. A of n equals, what was the first term? 100. What was the number we were multiplying by over and over again? 0.8 to the n minus 1. So if we wanted to use that to find the fifth path, we put 5 in here for n, and we would solve this out, right? Does this make sense?
Yes.
I hope so. It's a good one, you guys. I need you to at least get the first 10 problems done in class. If you, by chance, are somebody who is not running down notes, and then you have no clue how to do the very first problem, I'm going to have very little patience. Just saying. Your assignment then is page 427, 1 through 24.